Hello everyone, this is another video in which I will be explaining the sorting algorithms. In this video, I will cover the two sorting algorithms. First is the selection sort and another is the bubble sort. Rest of the sorting algorithms I will be explaining in the upcoming videos. So in this I will follow the approach in which I will be discussing what is the a particular algorithm or particular sorting algorithm and how it works, why it works, and then we will go to the implementation part of it and analyze the time complexity, and that's all. We will be following the flow in this. So first is the selection sort. So let me just give you an overview that what is the selection sort. Selection sort is basically a kind of selection of the minimum elements, and every time we find the minimum element and then we swap it with the front or position. So in the selection sort, what happens is that we are having the two parts. One is the sorted portion, another is the unsorted portion. So in this, what happens is from the unsorted portion, we just finds the or selects the minimum element and then we swap it with the front position. So whatever the unsorted portion is, we just find the minimum element, and whatever the minimum element we get, we swap it with the front element of the unsorted portion. And whenever we perform this in the repetition, in the number of passes, so whatever is the pass is, let's say we have performed the pass one. So in that, the one element will get sorted. In the second pass, two elements will get sorted. So likewise, if ith pass has been performed, then I elements will be sorted. So that's what I have mentioned here, that in the selection sort, what we have to do is we have to find the smallest element or the smallest item from the unsorted portion, and then we place it at the front. And again, when we have done this for the first pass, then we move to the second pass, and that we again find the next smallest. Again, we place it at the next. Means whatever the smallest element we have kept in the previous pass, next to that we keep the another smallest. So that's what we perform in the repetition. And when all the number of passes has been performed, whatever the number of passes are performed, you will see in the example, after that the entire array gets sorted. So the core idea of this is that every step we select a smallest element, as I have told, from the unsorted portion, and then we put it at the beginning of that part. So just see the unsorted portion, whatever the minimum element is, take that and swap it with the first position or the first element in the unsorted part. Okay, this is the core idea of the selection sort. So at each step, we just select the smallest element from the unsorted part and then put it at the beginning of that part. Okay, now let's see the example in order to have the more understanding of this. So this is the array. This is the example I have taken. It is array which is having some data, the elements 7, 4, 1, 5, 3. We have to sort this. So now selection sort, with the help of selection sort, how we can do this. So let's see what the strategy selection sort follows. The simple strategy is this: we are having the sorted portion and unsorted portion. In this array, we can see that the sorted portion is as of now empty. No any sorted data is present here. Now we have to convert it into the sorted form. So we can see that the entire array is in the sorted portion now. So what we will firstly do is we will firstly find the minimum element of all these elements. And when the minimum element has been found, that is 1 in this case, then 1 will be swapped with this first element. This is the first position of the unsorted part of the unsorted portion. Then when these elements will be swapped, this is the first pass has been done. Now move to the second pass, again perform the whatever the logic is there to find the minimum, and then again swap that minimum with the first position of the unsorted part. So in the second position, what will happen? This part will already be sorted. Now from second portion, we will see from this, and this will be the first position of the unsorted part where the next element will be coming. So let's see that in the pass one, what we will do. In the past one, we are already having this particular data. So in this, I will be initially at this port, at this position. Okay, I is now here, pointing at the 0th index. Now what we will do, we will start checking from this one index till the end index in order to get the minimum. We can also start from the I equal to 0 index. That will also work, but in my case, I am starting with this, that I am having this I at 0th index and going from 1 to end and seeing for any minimum element. So firstly, what I will do, I will keep this as the 0th index as the minimum element index, just assuming as of now. And when I will get the next minimum, I will just update this index. Okay, and at the end, whatever the element which I will get minimum, I will just swap it with this. Just let's go with the flow now. I is at the 0th index and I am checking for the minimum. So is for the minimum, 4 is the minimum, so this minimum index will be updated with this one index. Then again, One is the again the more minimum or the even minimum or lesser than the 4. So again this minimum index will be updated with the second index, and at the end till when we will complete this first pass, we know that this minimum index will be pointing towards this second index, so therefore it is containing the minimum element, and then it will be swapped with 7. So how the data will look like? The data will look something like this, that 1 is the minimum and 7 has to be swapped with this. So 1 will come at the 0th index, 4 will remain intact, 7 will come after swapping here, and 5 will be here, and 3 will be here. Now this is the result after the first pass. Now the second pass will be performed, and in this what happens is, now see, this is the data. Let me just keep it here, and these indexes here. Okay, so now this is the data. Now I will move to the next index, that is here. Now this is the updated part, this is the updated portion after the pass one. So I will move here. Now what will happen, we will start from this second index and go till end. We will find the minimum. Now whatever the element I will find as minimum, that will be as a minimum, and that will be swapped with this first, this particular portion. Or so we can also start from the starting from the ith index itself, because if no any minimum is found, then that will be, means in that case also the minimum will be found. And if we are doing this, then let's say if these all are the elements which are the greater than this, so no any change will be done, the minimum index will remain the same. So in this case, now 3 is the minimum, so 3 will be swapped with 4. So what will be the result now? 1, 3 will be coming at the place of 4, so 3 will come here, 7 and 5 will remain intact, and 4 will go at the place of 3. Again, let me just keep these indexes here. So these are the indexes, and now let's take this I ahead. Now I will move to the another index. Now I will just move to the another index, so I will come now here, and now what we will do, we will just see for the minimum in this particular part. So 4 is the minimum, therefore 4 will be coming at this seventh said this 7 element, and 7 will be going at the end. So this is for the pass 3, and in this pass 3 what will happen, 1 will come here, 3 will 3 is already here, 4 will come at the place of 7, 5 is there itself, and 7 will be going at the place of 4. Okay, let me just again take this indexes and keep it here. Okay, and now I will move again further, so I will move here, and now it will check for the further element. So this is the element, this is the only minimum, and we also know that out of this 5 is itself, so I will remain at the at minimum index will remain at its position itself, so no any swapping will be done here. Okay, so in the pass 4 what will happen is, it will remain same, 1, 3, 4, 5, 7. Okay, this is the case. So now we are able to see here that even if the array is already sorted, then in that case also we have to perform the number of comparisons, okay, for the in order to find the minimum element, if even if the minimum element is not like they are already in the sorted form. Okay, so we will have to find for the minimum even if the array is sorted itself, so that number of comparisons has to be done. Now we have seen that here the we were having the 5 elements in this array, and we have performed the 4 passes. So in 4 passes we have already got this. Now why we have not taken this I to the last index? Obviously because I am seeing this that if I'm taking if I'm taking I at the last index, then in that case there are no any elements in order to check for the minimum. Further it will take to the error, the runtime error, the out of bound index. Okay, so in that case I will not be taking this I will be I will be coming till this n minus 2 index itself. Even if you run for from starting from I, then also if you will try to see this I, and okay, now I have to find the minimum of this. Okay, so then also you will have to check for the elements. Yes, I have to find the minimum. So in that case no any change will be done, because for the one element, how you, what is the minimum, it is already sorted in itself, so no need to check for that. So I will be moving till the n minus 2 index itself. Okay, so this is all about this. And yes, we have seen for this that we were going from this 0 till n minus 2 index for I. So let me just write here that outer loop is running for what outer loop is running. Outer loop is running from I equal to, from 0, starting from 0 to I equal to what, I equal to n minus 2 index. Why not for till n minus 1 index? Because if you are starting from I plus 1, then also there are no any elements to check. And if you are also starting from I itself, there is no need to check for the one element itself, because it is already at the correct position. Okay, it is already sorted in itself, or we can say it is already the minimum, so no any point of swapping and all. So this outer loop will be running for I equal to n minus 2, and then if we check for the inner loop, so inner loop is running for what? See, when I is starting from 0, inner loop is checking from I plus 1 till the end index. So here j will be moving from j equal to I plus 1 to j equal to n minus 1 index for every particular pass. For every I equal to this 0, it will be moving from 1 to n minus 1. For I equal to 1, it will be moving from 2 to n minus 1. So that's what for finding the minimum element. Okay, now let's get into the code part firstly, then we will come to the more about this. So firstly, let me take the size of this vector. So this n equal to nums dot size. Okay, we have taken the size, and now what we have to do, we have to perform this operations. Sorry, this loop. So for int I equal to 0, I less than equal to n minus 2 we have to take, and then I plus plus. Now we again have to perform write one another loop in a loop, that is int j equal to, that is starting from I equal to, sorry, j equal to I plus 1, and then j less than n, and j plus plus, that is going till n minus 1. Okay, now what we have to perform is, currently I is at 0th index, we have to find the minimum element. What is the minimum element, so that I can swap it with the first element, or the first first position of the unsorted part. So in order to find the minimum element, I will have to keep a minimum index. Okay, I will be keeping the minimum index in order to get that index where the minimum element is already present. So at a start, what I will do, I don't know what is the minimum index where the minimum element is there. So that will be I will be just maintaining, I will be just having the starting index position as the minimum element. I'm just assuming. So as of now, I will be here, and now I will keep a check here, that if this nums of j, if I found that this nums of j is lesser than the nums of minimum index. Okay, if I found this, that whatever the element I am having, if it is lesser than the minimum index element, then just update that element, sorry, update that minimum index with what? The index j, because j is the index which is containing the even lesser element than this element which is at the minimum index. So this will be updated with this, and at the end, after completing the entire pass, what will be having, like in the first pass we can see that 0, this 2 will be the index, so it will be updated in the minimum index, because this is the minimum element in the entire array. So at the end, when this loop is completed, we will just swap the nums of I, obviously because I am at I equal to 0th index, and whatever the minimum element will become, it will be swapped with this. So nums of I, and with nums of minimum index, whatever the minimum index is, because it is containing the minimum element. So therefore the swap will be done with those elements. Now this particular thing will be performed for n minus 1 number of passes. Let's just take the input and run this. So 74153 is the input, size is 5, 74153. Let me just run this. Okay, so we have seen that this array is already sorted, like 1 3 4 5 7. Okay, now let's get into the time complexity part. Okay, then we will also discuss that why this is the only strategy which works. So the time complexity for this is, this outer loop is running from I equal to 0 to n minus 2, and for every I, this inner loop is running from I plus 1 to n. Let's observe this, how it is going. Okay, so let's write here for first time, or let me write this as pass 1. For pass 1, what it is happening, the loop is running from I plus 1 to n minus 1. It means when I is 0, it is running for 1 to n minus 1. We can say for n minus 1 times. Okay, so here it runs for n minus 1 times. Again, for next pass, for pass 2, Then when I becomes 1, it will run from 2 to n minus 1. 2 to n minus 1 means now it is running for n minus 2 times. So now it is running for n minus 2 times. And likewise, if we see for the last value, like I equal to n minus 2. N minus 2 means the last second index. And for last second index, it is running from like I plus 1. So last second index till n minus 1. It means it will only run for one time itself. Okay. So in this case, for the pass n minus 1, it runs for one time. So now if you see the comparisons, or if we see the summation of it is a kind of summation like 1 to n minus 1. Okay, so these are the number of times this particular loop is running. So for that we can see the summation of 1 plus 2 plus 3 plus and going till n minus 1. So this is what it is looking like. It is n into n minus 1 by 2. That is the kind of formula. Okay, so n into n minus 1 by 2 is nothing but n square. Okay, that's like n square by 2 minus n by 2. And if we see the time complexity, so it just dominates the greater value. So n square by 2 will be dominated, and also the constants are ignored. So because the constants are ignored, so the time complexity will become big O of n square. Okay, that's what the time complexity of this is. And that is for the best case, worst case, and average case all. Okay, there is no any like adaptive capability of here that it can be optimized in the best case. Okay, so now why does this particular strategy works? See what it is happening. We have just observed that at every pass, what is happening? One element is sorted in one pass. In the second pass, two elements were sorted. If you take another example, you can understand it more, like because it is just sorted in that manner. In pass 3, the 3 elements will be sorted. In pass 4, the 4 elements will be sorted. Now if you can see that at every pass you have taken the smallest element and put it at its correct position, then at the end you need not to check for the last element, because as of now you have already taken one by one the smallest element and put it at the correct position. Therefore the last element it will already be at the correct position. You need not to check for that. And even if you you can also understand that with that, if you start to check for this, then with what you will compare? If you are starting from I plus 1, or even you if you are starting with I, then there is no point of checking, because the it is minimum in itself, it is sorted in itself, it is at the correct position. So that's what that after I passes, the first I elements are the I smallest elements in the sorted order. Okay, so that's why it works. We have already seen the time complexity for this. There's the selection sort always scans the remaining elements to find the minimum. It always does. There is no point that if the array is already sorted, so it will not do. Yes, because it is must. It is compulsory for it to scan the remaining elements. Then only it will see that the array is already sorted, or it is having it is not sorted in order to swap the minimum element with the first. So it is always has to be done. So how many comparisons are made? We have already seen that, and firstly the n minus 1, then n minus 2, then n minus 3, and likewise till n. So the summation of this is simple, the mathematical formula n into n minus 1 by 2, which leads to big O of n square time complexity. So the total comparisons made were n square by 2, but if we see in the terms of time complexity, that will be like big O of n square, avoiding the lower values or the constant values. So in the best case, worst case, and the average case, the time complexity is big O of n square. Now also we can see the number of swaps. So in each pass, when this first pass is performed, this one is swapped with this 7. So one pass is performed, so 7 and 1 are swapped. Then in second pass, this 3 is the smallest, so 3 and 4 were swapped. So one pass is again performed. In pass 3, then this 4 was the minimum, so 4 was this swapped with this 7. So again one pass is performed. So at every pass, one swap is performed. So therefore we can say that if n minus 1 number of passes were performed in this case, so n minus 1 swaps will be made. So that's what we see in terms of big O of n. That will be the total swaps big O of n. Okay, only one swap per pass. Now some of the properties, like is it stable? So selection sort is not stable, because in that case, if you have found a minimum element, and if you are then swapping it with the first element in the unsorted portion, so there might be the case that the two elements which are equal, their order can be altered. Okay, it's like that. For example, if you are having the two elements, let's say in the array, uh, let's say 4 1 4 4 1. Now 4 is the present equal elements two times. So now if you see that in this part, now 1 is the minimum, So in that case, 1 will be swapped with this 4. So what will happen? 1 will come here. Okay, then 4 is already there, and 4 will then this one first 4 will be going there. So their relative order is changed. This 4 is already at this place. This 4 came at here. So that's why this the relative order of the equal elements changes. And in case if the minimum element is a kind of that which is swapping with the first element. So that's why it is not stable. And in place, yes, it is in place. Swaps we have already seen very few as lesser than equal to n, and comparisons always n square by 2. These are some of the properties in case of the selection sort. Okay, so we have seen the implementation code, all the implementation part also. Now let's get into the another sorting algorithm, that is the bubble sort. So in the bubble sort, what happens is we every time we takes the adjacent elements, we compares them, and if they are in the wrong order, then we just swaps both of those elements. So in the bubble sort, the simple idea is that every time take the adjacent elements. If they are in the correct order, leave it. It's okay. If they are not in the correct order, then just swap both of those elements. And at every pass, what happens is when you perform this in repetition for the number of passes, at every pass, the greatest element moves at the end. In the second pass, when you perform the another greatest element among that data, that will be moved at the previous of the whatever the greater element is at the last index. At the last second index, another greater will be there. Okay. That's how the bubble sort works. So that's what it is written, that it is the combination, the simple combination of that you see the adjacent comparisons and performing the adjacent comparisons, you can just swap those elements if they are in the wrong order. And what it does, it just leads to the biggest elements move to the right at each pass. So the core idea is simple, that the bubble sort compares the adjacent elements and swaps them if they are in the wrong order, as I have already told. And by doing this repeatedly, the large elements, it just bubbles to the end of the arrays. In the simple terms, it moves to the end of the array. Now let's see the example again. So now in this example, we are having this array, and now let's start the observation. How does it work? So this is the array, and the elements are 4, 2, 7, 1. We have to sort it using the bubble sort algorithm. Now firstly, these two adjacent elements we see, these are in the wrong order. They has to be swapped. So 2 comes here, 4 comes here. Now 4 and 7 will be seen. They are in the right order, no problem. Then 7 and 1 will be seen. So here 1 and 7 and 1 are in the wrong order. Again swap will be performed. So 1 comes at the second index, 7 comes at the third index. So it works in this way, that in the pass 1, firstly these two elements will be checked. So 4 and 2 in the wrong order, swap those. So 2 comes here and 4 comes here. And let's also take this in the way. 2 comes here, 4 comes here, 7 is already here, and 1 is already here. Now these two elements will be checked, that's in the correct order. Then these two elements will be checked, so wrong order. So 1 will be coming here, 7 will be coming here. So 2, 4, 1 and 7. Now first pass has been done. Now we can see that the greatest element is at the end. Okay, now let's move towards the second pass. In the second pass, again the same thing will be done. The comparisons will be made among these two elements. That is correct order, no problem. Again these two elements will be checked. The order is wrong, so it will be like 2, 1, 4 and 7. And after this, these two elements will be compared, so no problem, they are in the correct order. Now move to the another pass, that is pass 3. Now in this, again the adjacent elements will be compared. So 2, 1, they are in the wrong order. So 1, 2, 4 and 7. Again these two elements will be compared, so they are in the correct order. These two elements will be compared, they are in the correct order. So that's how it works. And again we can see here that these three passes has been performed for these four elements. Now let's just make a observation in this. Okay, so in this we can see that what is happening for these adjacent elements. Firstly these two elements are compared, then these two elements are compared, then these two elements are compared, and at the end of the first pass, the greatest element, that is 7, is at the end. Now because the greatest element is already at the end, so now in the second pass we do not need to go till the end, because the end index is already containing the greatest element. So now we have to go till the last second index, that is still n-2 index, and then for the another third last index. So that's how, because at every pass the greatest element is going at the end, so we have to just decrement that particular size of the array in order to check. So what will happen is, I have already mentioned here, how it is working. So in the first pass, we will be this loop will be running from 0 to n minus 1. It means from the first index till the end index. Okay. Now because the greatest element is at the end, then we will, in the second pass, we will loop from 0 to n minus 2. Then in the second pass we will loop from 0 to n minus 3, and at the end we have to be we should have the at least two elements at the because they are the adjacent elements in order to check. We cannot say that yes, only 0th index can be there so we can check there. No, we want the adjacent element, so we need at least two elements. So therefore for the last pass we will have to perform the loop from 0 to 1. Okay, so that's how, for what the outer loop is running. Outer loop is running from I equal to, the inner loop is running from 0 to I every time. Okay, or we can say in that way that 0 to I, and we can just run the outer loop from for that I equal to n minus 1 to 1, so that when I is equal to n minus 1, this inner loop can run from 0 to I, that is for n minus 1 till n minus 1. When I decrement it to n minus 2, it then inner loop runs from 0 to n minus 2. So in that way, let's just see the code part in order to understand more about this. So here again I will be taking the size of this vector, so that is nums dot size, and now in this I will be running the loop for int I equal to, now this will be from n minus 1, I greater than equal to 1, and I plus plus, sorry, I minus minus. And in this, why only till greater than equal to 1? It's because we have to have the two elements minimum in order to compare, that is for 0th index and for the first index. So that's why for the last pass we will have to go at least till 1. Okay, so 0 to 1, that's why I is going till 1. And now for the inner loop will be int j equal to, it will be starting from 0 always. Okay, and then j less than I and j plus plus. Let's see that why I am not going till n minus 1. See, if I will be going till last index, that is n minus 1, then for which next element I will be comparing? I want the adjacent elements, and if I do this, that I am at the last index and comparing with the next element, I am not having that index. Okay, that is like index out of bound. So I will have to go till the last index. That is, if I am having I as n minus 1, then I will be moving till I equal to this, from j equal to 0 to n minus 2, so that I can get the one element in order to compare. That's what I will be doing in the every pass. And here what I will have to do, now currently I am at the 0th index and I have to go till n minus 1, and every time I will be comparing the adjacent elements. So in that I will keep a check, and this nums of j, if it is greater than the nums of j plus 1, that means that's what the incorrect order is, because the in nums of j, this element is greater than the next element, and therefore I will have to swap both of them. So I will just perform a swap here with nums of j comma nums of j plus 1. Okay, that's what we have to do here. And now what will happen, just have a look at this, just run this for our example. I am taking this code here, let me put here. So now we are having this example here. I is now currently equal to n minus 1, that is till here last index. Now I will be taking my j 0. Okay, so j is currently here, and it is starting from j and going till n minus 2 last index, so that I can get the another next element to compare. Now just compare these elements. Nums of j is greater than nums of j plus 1, yes, so just swap these both elements. So it will become in this first pass 2 4 and 1 7, 2 4 7 1, and after that again j moves ahead. So when j will move ahead here, it will compare for these two elements. So j is this already, it is 4 and 7, so these elements are okay, no problem. Now j will move ahead. When j will move ahead, it will again see for the 7 and 1, so here the order will be changed. Okay, so here the another swap will be performed, that is 1 7. So after this first pass, elements will look something like this. Again for the second pass, they will look something like this. Then third pass, and the entire array will get sorted. So that's how this code is working. Now let me just take another value here, let's say 10, and let me just run this code. It will give the sorted order of this input. Okay, so what is the sorted order? That is 1 4 5 7 10. Okay, now let's check the time complexity of this. Let's analyze the time complexity. So I is as of now n minus 1, and for this n minus 1, j will be moving from 0 to n minus 1, or from less than I. So that will be from 0 to n minus 2. It means it is running for the n minus 1 times again. And then when I is n minus 2, this loop will be running from 0 to n minus 3. That's n minus 2 times. And if we see the last value, if I is equal to 1, then j will be running from 0 to less than 1. It means it will run for 0 only. That means for one time. So again, that's what the case we are seeing. So the time complexity in the average case and the worst case, that's what same as I have mentioned here, that firstly, the for the first pass, then it will be running for n minus 1 times, then for n minus 2 times, then for one time. Okay, so that's what the summation it gives us, big O of n square. Okay, so that's what the time complexity in this case. So this is now but only for the average case and the worst case. Now if we see in the best case, that why the bubble sort can be faster on the sorted arrays. So bubble sort can be faster on the sorted arrays. So if I was having this particular input array 1 2 3 4 5, now if I see, then for the first pass, like I will be n minus 1, so j will be moving from 0 to this n minus 1 index, this n minus 2 index. And now it will see that is this greater, is this the 1 greater than 2? No. 2 greater than 3? No. 3 greater than 4? No. 4 greater than 5? No. It means no any swaps has been done. So what I can do here is I can just put a flag here, and I will initially keep that flag as true, and later on whenever the swaps has been performed, I will just make that flag as false. Okay, see, I have already now performed the pass one. I have seen that no any elements were like in the wrong order. So therefore no any elements were in the wrong order. This condition has not been met anytime. Therefore these lines will not be executed, and if these lines will not be executed, therefore no swaps has been done, and flag will remain as true. It will not be set as false. So just before going to the second pass, I will just put a check here that if this flag is still true, just let me know that if the flag is still true, it means this condition has not been checked, has not been made as true anytime. Okay, and therefore the swaps has not been performed, and therefore the flag has all not been set as false. Therefore the flag is still true, and I will just break from here, break from the outer loop. I have not written inside the inner loop. I have written this inside the outer loop. So this statement when will be executed, it will break from the outer loop. Therefore, I will not be going towards the next pass, because I have in the first pass itself I have found that this entire array is sorted, and therefore because it is running for the one pass itself in the case of sorted array, so therefore it will run for the linear. It will just scan a linear scan will be performed. Therefore, in that case, the time complexity will be big O of n, because only n minus 1 comparisons has been made. That's, I can also call it as big O of n minus 1, and in terms of time complexity, the time complexity will be big O of n. So in the best case, what I am saying is that the time complexity will be big O of n. Okay, that's what we are seeing, and that this is the particular case which we can put here, like a early stop case, where I need not to find for the next of the passes, I not to check for the next passes. This is the early stop case. And for the stability, same as in the like in the selection sort, we have seen that stability in the selection sort was not stable, because while swapping those minimum elements, maybe the equal elements, their relative order may be altered. Okay, but in the case of so that's what it is not stable. But in the bubble sort, it not happens like this, like that, because we are checking for the adjacent elements, and if the adjacent elements are in the wrong order, in the and not in the correct order, so we are just swapping those elements. We are not making any alterations in the equal elements. Obviously, if let's say we are seeing for the adjacent elements, and both of those elements are in the uh, like they are the equal elements, so therefore they already are sorted, so we need not to make a swap there. Okay, that's because they are already sorted, so they will not be, their positions will not be altered. Only the elements, the adjacent elements which are in the wrong order, they will be swapped, so the equal elements never jump over each other. So that's what the line I have mentioned. In the bubble sort, it is stable. Why? Because only the adjacent elements are swapped, so the equal elements never jump over each other. Therefore, the equal elements will not, their order will not be altered, their order will not be changed. Okay, so that's what about the two uh, sorting algorithms, the selection sort and the bubble sort. Okay, we have seen the what is the what are these algorithms, what, how they works, and why they works. Okay, and we have also seen the implementation of those along with the analysis of their time complexities. That's all for this video. Thank you. We'll meet with the another sorting algorithms in the next video.